So what do we have here? Let's say that we have a graph, and you'll have to excuse my terrible drawing. Maybe I should get a new pad. So we have a graph. It's a path, the basic path. And we'll say that this is node A, this is node B, C, D, and we're just counting up to 3. And what happens? Let's look at it from the perspective of A. So A has a routing table, right? And at iteration 0, what do we have? Well, in this routing table, A has the other elements in the graph, the other vertices in the graph, right? So it has B, C, and D. Initialization step. It only knows about its neighbors. So in initialization, you just log the cost to get to its neighbors. So 1 hop, right? And that's 1, right? Because going from A to B is 1, and that's its only neighbor. Everything else is infinity. What happens in the second iteration? Well, what happens, remember we're assuming this is happening synchronously. So at the same time that this happened for all the other nodes, right? So in the second iteration, B knows about its neighbors, A and C, right? So it sends its distance vectors to its neighbors. So we're just going to look at A for this case, and we're going to look forward. But remember, the routing tables in each node have all the vertices in them. But we're just looking from the perspective of A and then forward. So for B, we'll just look at C and D. For C, we'll just look at D. And you'll get why in a second. So in the second iteration, what happens? B sends its distance vector information, so it knows about C. So it calculates the new distance. So for A, the B has the correct estimate in this case. It's just its neighbor, which is 2, and then the cost to go from A to B is 1, right? So that whole thing is just basically, you can summarize it by imagining that B is telling A that in order to get from C to me, the cost is 2, right? So we're just saying, I know where C is and it costs 2 to get there. It's telling A that in the second iteration. So that's 1 plus 2, and it's 3. So we have 3 here. But you'll notice that D is still infinity, because C has not, in that same step, C has told B about D, right? So you have to go to the second iteration, wherein A talks to B again, and B sends again its distance vector information, basically its routing table, and says, okay, I know how to get to D. I know how to get to D, and it costs 5, right, from me. My distance estimate is 5, because it does the same thing with C. So 2 plus 3 is 5, and then the cost here is 6. So this is sending over 5, and then we add this to it. We add this to it because we're talking to B, and B has 1 here. So 1 plus 5 is 6. So now we have completed the table for A. And this happens also with B, C, and D. So let's do that really quickly. So B, remember I said we're just looking at the ones in front of it for a particular purpose. So B to C, it already knows its neighbor. This is infinity. Then this next iteration, in the next iteration, B knows about 3 because remember, this is the initialization step, and then it tells B, hey, I know how to get to D. It costs 3 plus your value, so that, oops, pardon, I should put 5 there. Yeah, so 5, right? So 2 plus 3, 5 to get from B to D. And then finally for C, we're just looking at the one in front of it. It already knows. Now, you'll notice from A to D, in other words, to get all the information of the entire graph, it took 3 iterations. For B to get all the information, it only took 2 iterations, and for D, that is in front of it, right? And for D, it only took 1. Or pardon, for C, it only took 1. Now, D, it will take 3. As you'll notice, if you do it the other way, it'll take 3 because there's 3 hops here. Now, this is important for our analysis. But this is kind of how the thing works. Let's do a really quick example of an actual decent graph. So again, initialization step. We just look at the neighbors. The neighbors of Z, remember, this is from the perspective of Z. From the perspective of Z, we have 2 neighbors, V and X. So V is 6, right? Because it costs 6. And then for X, it's 2. But remember, all these other ones are infinity. We don't know them yet. In the initialization step, all we're looking at is the neighbors. The second iteration, the neighbors tell other neighbors their router table information, basically sending each distance vector over. So V tells Z about U and X. Right, so let's just start like this. So V tells Z that the cost to get to U is 1 plus your cost, right, which is 6. So this is 7, and it's a horrible 7. Okay. And X tells Z its distance vector information as well and says, look, my distance vector information for V is 3 plus your cost is 2, right? Plus your cost. So to get to V, it's cheaper than this, what we have here. So now it becomes 5. It also tells Z about Y. It says the cost here is 3. Right, so this is 5 now. And of course this stays the same. And then the third iteration, this whole thing happens again, and you'll notice basically V tells its information again, and to get to U from V, it costs 1 plus your cost, Z, which is now 5, remember, because we're going this way. So it's now 5, so this becomes 6. And that, you'll notice, is the end. Now, what's the furthest we can get? What's the longest path we can make without hitting previous nodes, right? It's 3. That's important for our time complexity analysis. So let's try to get an upper bound on that. if you can imagine, let's say we have just this big fat graph here with all kinds of random connections and stuff, but there's something about this graph, right? It has an incredibly ridiculously long path to a particular vertex. And the size of this path is far larger than anything in here, right? Well, you can imagine in any such traversal algorithm, that's just basically something like gossip, just hopping from node to node. How long would it take to get to the last, or which node would be the last one? Well, of course, everything here, every path you can think of here is shorter. So you'd have to go to this one, the last, because it's the longest one. Well, it's kind of the idea, right? As you kind of imagined in when we were doing the basic path. So let's say we have whatever topology here, but we're really interested in the longest path. We're interested in the longest path, and you can show pretty obviously. We're kind of gonna skip this step. It's really obvious that the traversal would a traversal algorithm would reach the last vertex in the longest path last, starting from the first vertex on that path. So let's say we have this, again, remember there's a bunch of nodes here, but we're really interested in the longest path. We have A1 along this path, A2, A3, all the way until A sub n, right? Now, from the perspective of A1, its routing table looks like this. A2, A3, all the way to A sub n. And remember, initialization step, it just knows about its neighbors. So let's say the cost, we're just going to count up, right? So the cost of this edge is 1, 2, 3, 4, all the way to n minus 1. So it knows about 1, but everything else is infinity. What happens on the second, the second iteration? Well, it already knew about 1. In the initialization step, A3 told, or you could say either way, A2 knows about A3 in the initialization step. So in the second iteration, A2 tells A1 about A3. So now A3, we have a cost of 3. But for everything after that, you still have infinity with respect to A1. What about in the third iteration? Well, you have A4 somewhere over here. In that iteration, A2 found out about A4. So now A2 can tell A1 about A4, which is 1, 2, 3. So 3, the cost from A2 to A4 is 5, 2 plus 3. And then the cost from A1 to A2 is 1. So A4 would be 6, right? So you can see where this is going. 1, 3, there'd be a 6 here, and then infinity. So let's suppose this. Let's say, well, let's just make a claim. I'm not going to waste time writing it. Basically, that all along this the longest path it takes k minus 1 iterations to get all the information on the beginning, the routing table of the beginning vertex, right? So we suppose that we say that our base case is 1, so that is 1 hop. What happens in 1 hop? Well, initialization step. So we already know. So let's say initialization step. we know it's 1. So let's suppose this is true for k minus 2 iterations. What happens on the k minus first iteration? Well, because of our induction step, our induction hypothesis, we know that the first, remember, this is with respect to the beginning vertex on this longest path. Because of the induction hypothesis, we know the value of the k minus second edge away from A1. And we know that since A1 to AK minus 2, that the number of hops is less than or equal to k minus 2, that means A1 has to know the information of A sub k minus 2. If A sub 2, the distance from A sub 2 to A sub k minus 1 is within the iterations of our induction hypothesis, so we can assume that it knows up to k minus 2, meaning it knows about k minus 1. So all we have to say is, since that is true, A sub 2 just has to tell A sub 1 about k minus 1, and so we know about k minus 1 in the k minus first iteration. So we've established that for the longest path. Then there would be another path somewhere else, because it contradicts our theorem. So we'd have this path E, but it wouldn't make sense because you can't have more than the cardinality of the edges in this graph. You can't have an extra path here because then that graph would have an E such E prime where E prime does not equal E, right? So you can see basically this works out. So a general graph, well, in the conventional Bellman-Ford analysis, we just have, there's a bunch of other stuff. And every node, this is iterating on one machine, basically. And why that's important is really, like, if you want to formalize this a bit, you could imagine that actually there were a bunch of Turing machines operating at the same time for our previous analysis, and that's why we're allowed to do that. But in this case, we're only using one to operate on this graph. In that case, well, then we'd have to look at this vertex and then get this information, and that's one iteration. And then this one giving its information here, that's 2 iterations. This one giving its information here, 3 iterations. This one, 4 iterations. However, we're not even finished. We have to get, that's kind of like this whole thing would be happening in parallel in our previous analysis because of our assumptions. But we still have to get this in this. Well, in this case, it wouldn't be, but remove this. In that case, we'll have another iteration to get this, which knows about this now, to here. And it would still probably go on because it would still need to converge everywhere, and it can't assume that it stopped. And there's a bunch of other stuff here. So it would keep going. We would go 5, 6, 7, 8, etc. And so how many edges do we have here? So we have 4 edges, 4 nodes. You can kind of see how this is This is basically the same analysis as our distance vector analysis, except it's not being done synchronously. So that means that we have to now look at every node iteratively, right? So it's not that we have a bunch of routing tables at the same time and we could just update them in the same iteration. We have one routing table, one iteration, another routing table, another iteration, and there's as many routing tables as there are vertices. And so you can see how this could easily be shown to be the cardinality of the vertex set times the cardinality of the edge set in order for the Bellman-Ford algorithm to converge, right? Because again, distance vector is basically a Bellman-Ford algorithm. Again, just imagine that we were doing the previous analysis, except now you don't have the power of parallelism. You have to do everything iteratively. So look at this node, then this node, then this node, then this node, and we're counting that the operations individually now. So you can see, this is basically for you to like get a springboard to jump off of to easily prove that Bellman-Ford is worst case